So this is going to be a skills video where we think about how do you relate things like equilibrium concentrations to free energies and equilibrium constants. So let's get into that. So when we're talking about bonds, we often talk about things in terms of energies, right? We might say the energy to break a hydrogen bond is 20 kilojoules per mole. But then when we talk about an experiment or we talk about biological context, we often talk about fractions. Like we might say that in a cell, 90% of the hypothetical ACE molecules are in the folded form. And so the question is, how do we relate these to one another? Pretty typical way to relate these is using this expression delta G naught prime equals minus RT log of KEQ. In a future video, I'm actually going to derive this in the context of how I normally think about things, which is free energy as a bet. But for now, we're just going to take this as a given and just use it as a tool to ask questions that we want. The question we're going to be asking is how much energy does it take to put a positive charge in the hydrophobic core of a protein? And you might remember this, maybe you've seen in one of my videos that, or other places, that the core of proteins tends to be a bunch of hydrophobic residues. The outside tends to be a bunch of polar and charged residues. We're going to just say, how important is that? And try to jam a positively charged amino acid inside a hydrophobic core and see what happens. So the system we're going to do this in is one I talk about a lot in my videos, staphylococcal nuclease. This is an enzyme that folds to a particular structure, but then is in equilibrium with an unfolded form. So we have an equilibrium between the folded form here and the unfolded form. I'm writing this with the unfolded form as the products. So a negative delta G suggests that the protein is favoring unfolded. So the equilibrium constant for the reaction is just the concentration of U at the unfolded, the unfolded at equilibrium versus over the folded at equilibrium. Okay, so here is the amino acid sequence of staphylococcal nuclease. I've written it in their one-letter code. So if you know all of your amino acids, you say this is methionine, leucine, valine, etc. To make it a little bit more chemical, here we've got a methionine, a leucine, a valine, a methionine. I'm not going to keep going through all of them because it would be a very boring video, but we'll go to the very end and we'll say, look at the very end. Whoop, I can't. We've got an aspartate, a serine, a glycine, and a glutamine. Okay, so that's the amino acid sequence. What are we going to do? We're going to use a genetic trick to convince or to engineer this protein so that at position 92, we're going to take what is currently an isoleucine and we are going to convert it into a lysine. So what is isoleucine? Isoleucine is a very hydrophobic amino acid. I'm showing it here with it's got 1, 2, 3, 4 nonpolar carbons. So it's hydrophobic, does not like being around water. And we're going to drop in a lysine, which does have some carbon, 2, 3, 4. In fact, it has the same number of nonpolar carbons. But then it's got this positively charged amine at the end. And so we're going to say, what happens? So yeah, you can see I took the I and I turned it into the K. Let's make that a little bit less subtle. Apparently I can't switch slides when I'm zoomed up. So that's now a K. Okay, cool. Position 92 is actually in the hydrophobic core, as I hinted at earlier. And so here in pink, I've highlighted the amino acid there. And then what I'm showing here is the lysine as a pink residue, where I've sliced into the core of the protein so we can sort of see where it is. And I've colored all the amino acids according to their overall hydrophobicity measured on a quantitative scale. So going this way, it becomes more and more hydrophobic. And so, yeah, this is a good point to pause and think about things before launching into a bunch of sort of manipulations here. What effect is this going to have on the structure? What's your prediction? So good chance to pause and think about it. So pause. Okay, I'm assuming you're coming out of your pause. I'm not going to answer it right away. We're going to get there with our calculation. So, okay, now we're going to do an experiment to ask this question. And what we're going to do is we're going to experimentally measure the concentrations of each of these conformations. We're going to do so using spectroscopy, which basically means we're going to shine light in at various lengths, and we're going to measure the effect of how this interacts with the light by various modalities. And from that, we can actually learn things about the concentrations of these two molecules. I should actually do some videos on that someday. There's also all kinds of cool things that we can do. But for now, we have a technique that lets us measure concentrations, right? We can say how much of the folded form, how much of the unfolded form is in solution under a given set of conditions. And if you do this experiment, what we get is that the folded form, sort of normal lab conditions, is at 1 × 10⁻⁵ molar, whereas the unfolded form is at 5.8 times 10 to the minus 14th molar. And so this has a much, much lower concentration than this, right? Many orders of magnitude lower. All right, cool. What do we do with that? Well, let's turn this into a free energy. We're going to turn this into a delta G naught prime using this equation here. And so delta G naught prime is basically going to tell us which direction of the reaction is favored when it equilibrates, right? So we're going to say, does it favor product? Does it favor reactant? This free energy now is going to be telling us which side is favored, all else being equal. Okay, how do we do it? Well, you can see the math here. So I will let you, if you want, you can pause and figure it out, or you can try to do it while I'm doing it, because I'm going to do it right alongside y'all. So what I've recognized here is that KEQ is right there, so I can substitute in this. This is just the definition of a KEQ, right? It's the products at equilibrium over the reactants at equilibrium. I've got measured values there, so I can basically write out this, delta G naught prime equals minus RT log of UEQ over FEQ. And that delta G, I can then just substitute in numbers, right? I can say that equals minus 0.008314 times 298 times the log of U, whoops, I should write in the number, of 5.8 E minus 13 over 1.0 E minus 5. Okay? So that's the math. If you plug in those numbers, what you get is you get positive 41 kilojoules per mole. Make sure I'm not cutting that off. I'm not. Awesome. So positive 41 kilojoules per mole for this reaction. So it's positive, which means that this favors the folded form, right? So I should go back to our definition of the equilibrium somewhere. Well, should put it that closer. Sorry. Wow. Okay. There we go. The folded form, right? So it's saying it favors, at equilibrium, the system will favor the products. It will favor the folded form. All right, get to go back through a bunch of slides again. Woohoo, so fast. Okay, there we go. Positive 41 kilojoules per mole. Oh, hey, Pat, it's right here. Favoring the folded form. Okay, cool. Now we introduce the I92K mutation using molecular biology. We make the protein, we put it in the lab, we put it, and we do our spectroscopy experiment again, we measure it, and we see it as a new set of concentrations. And so now the concentrations have gone to 10 to the minus 11 over here and 10 to the minus 5th here. So big change in those concentrations. Again, we can just plug these numbers in. So we already had our expression for that. So it was minus 0.008314 times 298 times the natural log of, I got to get our signs right, 1e minus 5 over 7.2e minus 11. Okay? So I just did some plugging and chugging. And if you do this, you get equals minus 29 kilojoules per mole. So what is that saying? This is a delta G naught prime, so it's talking about the equilibrium state of the system. It is saying the equilibrium state favors the unfolded form, right? It's minus. So if we were to, another way to think about a delta G naught prime is if you make everything 1 molar, and then you say, what's our free energy there? It's saying our free energy will be negative, that we're going to have to see a lot more positive, forward reactions than reverse reactions. So it's strongly now favoring the forward direction. So what's the energetic effect of the mutation, right? So this is where we get to when we say, oh, a bond is worth this. How do we turn this into the energetic effect of the mutation? So here's the numbers. Why don't you think about that for a second if it isn't obvious? How would you turn this into an energetic effect? So you can pause if you want. I'm assuming you paused. Let's unpause. So what we're going to do is we're going to calculate this number here, the delta G. Gotta love proliferations of delta G's. This is basically saying what is the difference in the delta G's. And a convention in biochemistry and most of chemistry is to put the perturbed one first. So we're saying what happened when we perturbed it. So this would be the delta G naught prime of I92K minus the delta G naught prime of the staph nucleus, the initial molecule. You get a delta G, right? Because this is a delta, a difference in 2 delta G's. As a fun aside, I was definitely involved in a paper where we did a delta G with 5 deltas. Yeah, so you can go completely nuts with this idea. But okay, so we can just do this. We can do the math. So we can say minus 29 minus 41, right? So we just substitute in those numbers, and that gives us, I can do the math in my head, that gives us 70 minus 70 kilojoules per mole. So the energetic effect is minus 70 kilojoules per mole. So what does that mean? Oh look, I did it with not my handwriting. Okay, minus 70 kilojoules per mole. What does that mean? What it means is that replacing I-92 with lys-92 shifts the equilibrium by minus 70 kilojoules per mole. It's basically taking the equilibrium from in the initial system, favoring this form by plus 41 kilojoules per mole, to now it's favoring this form by minus 29 kilojoules per mole. So this one amino acid change, basically this change to the addition of an NH3 plus, it had a massive shift in the overall population of the system, going from preferring folded to preferring unfolded. And so an interpretation of this, at least a draft interpretation, would be that it takes 70 kilojoules per mole roughly to bury a charge in a hydrophobic core, or at least to bury a lysine in this particular hydrophobic core. So that's a pretty big energetic cost, right? I've talked before about how a water-water hydrogen bond is worth about 20 kilojoules per mole. So this is about 3 hydrogen bonds worth of energy just to take a charge, which was happily fulfilled in water in the unfolded state, and then drag it into the core of the protein. And I think this is a really good example of something I've talked about in other videos. That's when a protein folds, or when two molecules bind together and they're basically excluding solvent with some hydrophobic interaction, all of the polar contacts have to find a partner, because if they don't find a partner, it's just so energetically expensive to pull them out of water that they'll always favor the unfolded state in this case. Okay. So hopefully what you've seen now is that we have this way to interconvert between free energies and populations. And it's this simple relationship that the standard state free energy is equals minus RT log of the equilibrium constant. And then we didn't actually do it here, but if you flip it over with your log rules, you can get that the equilibrium constant equals minus RT log of the minus delta G, the standard state free energy over RT. And so over and over, we encounter this in biochemistry where we say, oh, look, a drug's binding constant is this, and it changed by this much. What's the energetic effect of that? So hopefully this gives you a way to start thinking about ways to convert between energies and populations in a meaningful way. All right, so that's what I have. Thanks again for watching, and have a great rest of whatever time of day it is for you.